Hi, it's me, Tim Dodd, the Everyday Astronaut. I'm in Mississippi at the Infinity Science Center, just outside of NASA's Stennis Space Center, and I'm here to check out a rocket engine. But not just any rocket engine. There's a very special rocket engine here that's kind of inside out and promises to be as efficient at sea level as a sea level engine and as efficient in space as a vacuum optimized engine. Welcome to the Aerospike. And with engineers relentlessly trying to optimize rockets in a world where even a 1% improvement is a massive leap, the Aerospike engine seems like a dream come true. Throughout history, there's actually been a number of Aerospikes that have made it really far into development, but to date, none have ever really flown, let alone been used on an orbital class rocket. If they're so good, why isn't everyone using them? Or for that fact, why isn't anyone using them? Why aren't these brand new engines like SpaceX's Raptor engine that are built from the ground up? Why aren't they Aerospikes? So today we're going to look at the history of the Aerospike engine, and then we're going to look at how nozzles work, including things like overexpansion, underexpansion, and expansion ratios. Then we'll look at the pros, the cons, the physical limitations, and the problems of the Aerospike engine. Then we're going to compare the Aerospike to other traditional rocket engines. But that's not all. I actually got some never before seen photos and videos of some historical Aerospike engines. Then I went out and talked to some people who have actually worked on and engineered Aerospikes. Then we're going to look at some compelling concepts and promising prospects for some future Aerospike engines. And hopefully by the end of this video, we'll know whether or not the holy grail of rockets is just waiting to be utilized, or if they're just simply not worth it. So put on your favorite Aerospike engine t-shirt, grab some popcorn, a drink, and a notepad, because this is a really long video and we have a lot to cover. So let's get started.
3, 2, 1,
That's one small step for man. Contact with a test 1.
So those of you that follow me on Twitter have probably been watching this video come to life and have likely noticed my tone change from Aerospikes suck to a little more neutral stance on the subject. Does this mean I'm maturing? And wow, after literally months of research, this turned out to be a monster. I mean, we ended up going through dozens and dozens of hard to find documents to be able to track down the actual numbers from their sources from some of these original papers back in the 60s. And although it took me a while, sorry, the more I learned, the more I realized just how much more I needed to learn and the more context I knew would need to be in this video in order to make it more understandable. So in order to make this more digestible, here's the timestamps of the major topics. And I've got links to those timestamps in the description, and like all my videos, I actually have a full article version up on my website, everydayastronaut.com, if you want to be able to search for certain sections or see some numbers later on. And again, the link's in the description. After I posted my Is SpaceX's Raptor engine the king of rocket engines and Why SSTOs Suck videos, I got so many people claiming that the real holy grail of rockets is actually the Aerospike engine. And you're not wrong. I mean, an engine that magically, thanks to physics, is inherently more efficient at almost any altitude. An engine that works as well at sea level as a perfectly tuned sea level engine bell and still performs just as well in a vacuum as a large vacuum bell. Wow, yes, sign me up. Why isn't there more love for the Aerospike engine in the aerospace industry? I mean, after all, SpaceX engineers tackled the ultimate challenge by developing a methane-powered full flow stage combustion cycle engine. If they could solve that crazy engine, why didn't they try for an Aerospike? Something that promises some pretty substantial gains, and they've already been fully developed. After all, Aerospikes definitely aren't new. They actually go all the way back to the 60s when engineers were looking for ways to improve upon some early rocket engines. Now, keep in mind, the engines at this point in time were relatively primitive, so the promise of an Aerospike engine was extra appealing. Perhaps the most notable and promising Aerospike was an Aerospike version of the J2 engine that powered the second and third stage of the Saturn V. This was called the J2T, and on paper, it seemed to be a nice and compact version of the J2, while offering even greater vacuum efficiency than the standard J2. Although it hit the test stand 34 times and had some promising potential, it was shelved alongside the Saturn V and any potential upgrade path thereof once the Space Shuttle program began. But it was actually considered for use as the Space Shuttle's main engine, But as we know, NASA went with a closed-cycle Bell-nozzled engine, the RS-25. Rocketdyne also took spare parts from the J2 and the simplified J2S rocket engines and developed a linear Aerospike engine known as the L1 linear testbed from 1970 to 1972. And it had 44 tests with 3,113 seconds of operation. But it'd be almost 30 years before the concept would be dusted off again and looked at with any serious consideration. And this time, it was for a space shuttle replacement known as Venture Star. The Venture Star was a rocket nerd's ultimate dream rocket. A single stage to orbit, or SSTO, fully reusable spaceplane that was to utilize a linear Aerospike engine called the RS-2200 that not only made it look like the Millennium Falcon, but it also promised nearly the same payload capability to low Earth orbit as the space shuttle it was intended to replace. In order to minimize risk, Lockheed Martin began development of a suborbital demonstration version of the Venture Star called the X-33, which was to use a smaller testbed version of the RS-2200 called the XRS-2200. It was fully operational and had accumulated 17 tests and about 1,600 seconds of test stand operations. But because of the overly ambitious use of super advanced carbon composite tanks, a few other technologies that had yet to be perfected, and some interesting politics, Lockheed Martin may have bit off a little more than they could chew. The Venture Star program and the X-33, along with the RS-2200 and the XRS-2200 linear Aerospike engines, were put on the shelf in 2001. Okay, so what the heck? Is the Aerospike just a bad luck engine, being assigned only to programs which were destined to be canceled? Why aren't any of these plans being resurrected now with more modern technologies? Well, let's first get into how they work, and in order to do so, we should probably do a quick overview of how and why a traditional Bell nozzle works, so we know how to compare them against Aerospikes. I mean, after all, the physics are the same between the Aerospike and a Bell nozzle, so let's dive in. Rockets work by taking a high pressure gas with molecules traveling in all directions and turning that pressure into high velocity flow in a very specific direction. And if all things are going smoothly, the direction of the flow is exactly opposite of the direction that the rocket is pointing. As we talked about in my video about the Raptor engine, the chamber pressure in rocket engines can be unbelievably high. SpaceX's Raptor engine is currently the king of chamber pressure at 270 bar, and they're aiming for 300 bar. Just to put into perspective how much pressure that is, it's like putting a BMW 740i sedan, which weighs nearly 2 tons, and placing it on something not much bigger than an average size US postage stamp. That's how much pressure is pushing down on every single square inch of the combustion chamber. To convert that pressure, engineers developed something called a converging diverging nozzle, or a de-Lavelle nozzle, that converts those high pressure gas molecules traveling in all directions to a high velocity gas moving in one direction. Now we're gonna go to Fluid Dynamics City here real quick, and not just any old fluid dynamics, but some super nutty stuff where everything gets backwards and upside down, as we're going to transition from a subsonic high pressure hot gas into a supersonic, lower pressure and cooler gas. So if our combustion chamber was just a tube coming off the injector, we'd end up with some hot gas moving out pretty fast, but not supersonic. And a fun reminder here about rocket engines and rocket engine efficiency: the faster the exhaust gas is ejected, the better. So in order to accelerate a gas moving through a tube, we can actually shrink the size of the tube. The same amount of mass will pass through this smaller area, and in order to do so, it needs to speed up. I think the best example of this is a standard old garden hose. Turn it on and put your thumb over the end of the hose. Now, ignoring a few potential losses, the same amount of water will flow through the hose regardless of if your thumb is covering the end or not. The only thing that changes is the water has to speed up to move the same volume of water through a smaller hole. Now remove your thumb and the water slows back down. But both methods would actually fill a bucket in the same amount of time. One will just be a lot splashier than the other. So the same thing applies with gas passing through a tube. We can keep shrinking the tube until we get to the point where the gas is traveling at sonic speeds, or the local speed of sound. Now I say local speed of sound because the speed of sound goes up with the square root of temperature. And because temperature in a rocket engine is really high, the speed of sound at the throat can be 5 to 10 times faster than that of room temperature at sea level. Once the exhaust gas is traveling at the speed of sound, we can't actually shrink the tube anymore because Here's where things get quite literally backwards. Once a gas is traveling at the speed of sound, if you shrink the tube anymore, you simply end up choking flow. So from this point on, engineers designed the nozzle to be the perfect shape, which will convert thermal energy into kinetic energy. So as the walls of the nozzle get wider, it actually accelerates the gas, and the pressure and temperature will lower. If you keep going with this and you make the nozzle big enough, you'll get to the point where the exhaust is actually at the same pressure as the ambient air outside, or in the case of sea level, 1 bar of pressure. It's actually kind of amazing to me that we can go all the way from hundreds of bar of pressure down to less than 1 bar in such a relatively short distance. And it's also weird to me that even though the exhaust gas is moving at unbelievable speeds, the exhaust pressure can actually get really, really low. And the lower pressure we can get that exhaust gas, the more we'll have converted high pressure into high gas velocity, which is desirable. But as a rocket climbs in altitude, the ambient air pressure outside of the rocket lowers. So the pressure at the end of the nozzle becomes higher and higher than the ambient air pressure outside of it. You can see a rocket's exhaust plume expanding out in all directions as it ascends into the vacuum of space. This is why vacuum optimized nozzles are so freaking big. The perfect example of this is SpaceX's Merlin engine, which has the same combustion chamber between the sea level version and the vacuum versions. The sea level version with its sea level nozzle is small enough that SpaceX can fit 9 of them inside the 3.7 meter wide Falcon 9. But the upper stage vacuum engine has only 1 engine because the vacuum bell's nozzle is about 3 meters wide. Just look at how snugly it fits inside the inner stage of the Falcon 9. You can tell whether or not a nozzle is optimal for its altitude by looking at the exhaust coming out of the nozzle. A nozzle that's perfectly matching the atmospheric pressure will have exhaust shooting out straight in a perfectly expanded plume or a perfect column of flame. Now, if a nozzle is too small for the altitude it's at, it's called being underexpanded. And you can see the exhaust gas immediately getting wider and wider as soon as it exits the nozzle. If the exhaust gas is traveling away from the rocket at all, that's energy literally being spent thrown out the sides. You want the exhaust traveling as straight as possible. At sea level, nozzles are virtually always too big, and that's called being overexpanded. You can tell when a rocket's nozzle is overexpanded because the exhaust gets squeezed tighter by the ambient air as it exits the nozzle. And it will even form shock waves as pressure grows and expands and then compresses again. These are called mock diamonds or shock diamonds, and although they look super cool and super pretty, they're actually a sign of inefficiency from an overexpanded nozzle. So now you might be thinking, why don't they just use vacuum optimized nozzles at sea level? Since rockets only spend their first few seconds at sea level, ambient air pressure drops in half by only about 5,000 meters or so, and they spend most of their time in the vacuum of space. Well, there's a few reasons, but first remember, the further away the nozzle exit pressure is from the ambient air pressure, the less efficient it is. So a sea level engine in a vacuum is inefficient, and a vacuum engine at sea level is inefficient. But there's actually another even bigger reason why you can't actually use a vacuum engine at sea level. It's because the nozzle would likely break due to something called flow separation. This is where the ambient air squeezes in against the flow of the exhaust, and it actually climbs up into the nozzle. And it does this so much that it can create these sudden shock waves and sudden pressure spikes called flow separations, which will most likely damage the nozzle. A nozzle can really only go down to about 40% overexpanded before you get flow separation. Well, that is unless you look at the space shuttle's main engine, the RS-25, which used a unique trick to curl the nozzle walls in ever so slightly, which allowed them to get down to about 14% overexpansion without flow separation at sea level. This allowed them to be very, very overexpanded, which made them more efficient throughout the entire 8.5-minute ascent, since they fired from sea level and they stayed running all the way into orbit. And considering how little amount of time is spent at sea level, maximizing nozzle design for the vacuum of space was definitely a good thing. But for some reason, it's still really weird to think that just regular old air at sea level can be higher pressure and actually squeeze in on rocket exhaust. But the pressure at the tip of the nozzle is actually pretty low. It's just moving very, 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 very fast. And even if you have a huge vacuum nozzle like the Vacuum Merlin 1D, it's still too small for the vacuum of space. If it were to match the ambient vacuum pressure, the nozzle would need to be infinitely long. And since that doesn't sound like it'd be very lightweight or fit inside of our universe, Engineers find the happy medium between packaging, mass, and performance. The term for how big the throat of the combustion chamber is compared to the exit of the bell is known as the expansion ratio. This is the ratio between the area of the throat versus the area of the nozzle exit. Again, for ease of reference, let's look at SpaceX's Merlin engine, which has the same chamber and throat diameter, but with different bells. A sea-level Merlin has a nozzle that's 0.91 meters wide, whereas the Merlin vacuum engine has a 2.89 meter wide nozzle. Since both engines have the same throat of 226 millimeters, this means the sea-level Merlin has an expansion ratio of 16:1, while the Merlin vacuum engine has an expansion ratio of 164:1. I think we all tend to look at a rocket engine's nozzle and go, hey, look at that huge rocket engine, when really we're seeing the most insignificant piece of the engine. As a matter of fact, many of the rockets we see on display are missing the actual engines or the turbopumps, and they just have dummy mock-up nozzles. So the next time you hear someone say, check out those huge engines, you can put your glasses up on your nose and say, the final size of the nozzle has only to do with the expansion ratio of the engine bell, and it does not necessarily correspond to the output of the engine. It's kind of like pointing to the wheels of a car and saying, look at that engine, because it's just like how the wheels of a car transmits the energy of the engine to the road. The nozzle converts the energy of the rocket engine into workable thrust. Okay, so you can't really fire a vacuum optimized engine at sea level. And this really is where Aerospikes come in. The idea behind Aerospikes is you allow the ambient air pressure to actually form the walls containing the flow of the exhaust, so it's always in nearly ideal conditions at any altitude. And not only will you not destroy your engine by lighting it at sea level, it's actually going to perform pretty darn well. And again, I know it doesn't really seem like it because it's just what we're used to, but at sea level there's actually an awful lot of air around us. And you don't really realize how much force it exerts until you remove air from something and you see how much force the atmosphere can actually apply. So with an Aerospike, the throat of the combustion chamber, or chambers, aims the exhaust gas at what is essentially just a slice of a traditional bell. When the engine is at sea level, the higher pressure ambient air outside of it pushes the lower pressure exhaust against the wall. So now instead of the ambient air pressure squeezing in on the exhaust and pushing it away from the nozzle wall, the ambient air pushes the exhaust further into the nozzle wall, which makes flow separation physically impossible. As the vehicle climbs in altitude, the ambient air pressure decreases, and so does the pressure on the exhaust flow. This essentially makes the wall that holds the exhaust grow, changing its expansion ratio with altitude. So really the air, or the lack of air, forms the outer wall of the Aerospikes, and due to the atmosphere getting thinner and thinner as the rocket's altitude increases, the virtual nozzle actually grows with altitude. But there's still an expansion ratio for Aerospike engines, and this is based on how long the spike itself is. The exhaust needs to form against the spike, and once the spike's gone, the exhaust will expand out beyond it in a vacuum, just like a traditional bell. Most Aerospike concepts have a flat base at the bottom, or a truncated spike, which takes the turbine exhaust and puts it through a heat exchanger, and that creates a pressure zone in the wake of the rocket that actually adds a little bit of additional thrust in higher altitudes, further aiding in the traits that are considered advantageous. In order to make an Aerospike engine, you need a differently shaped combustion chamber than a traditional one, or multiple chambers that form the unique shape needed to make an Aerospike. There's two main types of Aerospikes. There's the toroidal Aerospike and the linear Aerospike. With the toroidal Aerospike, the combustion chamber is like a donut, kind of, and the throat is an opening pointing inwards-ish towards a spike. A linear Aerospike has rows of combustion chambers that all point onto a flatter wedge-shaped ramp, and has at least two sides, and the exhaust ends up meeting each other at the tip. Most rocket concepts that utilize an Aerospike engine are single stage to orbit concepts, and that is a rocket that is only one stage and goes straight from sea level to orbit with no separation events. Now, I've already done a video on why SSTOs suck, and trust me, they're super cool. Like, yes, I want that, and maybe someday we'll have it, but physics just simply dictates that there's a lot better uses of rockets. I mean, after all, if the key is truly reuse, not putting the entire vehicle through punishing reentry forces is a good place to start. That's why we're seeing fully reusable concept like SpaceX's Starship be a huge multi-stage vehicle. But an Aerospike is a pretty good way to do a single stage to orbit rocket, since you can essentially utilize a vacuum optimized engine at sea level, and not only will it not explode, it'll operate about as well at sea level as a sea level optimized rocket engine. By the math, here's where a working Aerospike can nearly double the payload capacity of an SSTO compared to a good bell nozzled engine. But more on that later when we'll look at whether or not an Aerospike truly is the best option even for SSTOs. Okay, so other than SSTOs, in general, if Aerospikes are so great, why isn't it being used on every rocket? I mean, especially on first stages, where the vehicle transitions from sea level up to vacuumish conditions. Well, there's two main issues that plague Aerospikes: weight and heat. Let's start off with heat, as it's actually perhaps the biggest issue and contributes to less than ideal performance and additional weight. That's right. Now, despite looking like there's a lot less to cool, an Aerospike engine actually has a horrendous time keeping itself cool. I mean, after all, a rocket engine is basically just getting exhaust gas as hot and high pressure as you can, and eventually make it all move in one direction without it melting the engine trying to contain and direct it. And an engine melting, well, means you no longer have an engine. And as soon as your rocket no longer has a working engine, it tends to fall right back to Earth in a hurry. The primary way most liquid-fueled rocket engines cool themselves is through a process known as regenerative cooling. This is where liquid fuel is actually piped through the walls of the combustion chamber, and actually most of the nozzle as well, in order to cool them down. There's also some other tricks that rocket engines can do to keep themselves from melting. There's film cooling with fuel or exhaust, ablative cooling, and even radiative cooling. Ablative cooling, like how a heat shield typically works, is where you allow parts to sublimate or ablate, and in doing so, they take heat away with them. A good example of this is the RS-68 engine that powers ULA's Delta IV Heavy and powered the now retired Delta IV. Although it runs on liquid hydrogen just like the space shuttle, its exhaust isn't clear like the space shuttle's main exhaust. Instead, it has this orange glow to it. That's actually from the composite nozzle that uses graphite to ablate away, which takes the heat away with it. This is a little less common in modern liquid-fueled rocket engines, and it's of course not a good choice if you plan to reuse your engine, since you likely would have burnt through the majority of it during flight. Film cooling can take a few forms, either by injecting additional fuel inside the combustion chamber along the walls to keep those areas cooler, by pumping cooler exhaust down along the nozzle, or both. We've touched on the gas generator exhaust before in my video about Raptor engines, but the exhaust from a gas generator or preburner is relatively cool since it needs to be a low enough temperature for the turbine to be able to survive being subject to it. It's just super weird to think that you can take hot exhaust like 1000 Celsius, mix it with hotter exhaust like around 2500 Celsius, and actually end up somewhere between the two temperatures. My dumb brain tends to think that if you add those two together, it's the sum of those two numbers and not the average. I guess it's a good thing that I'm not a rocket engineer. But hey, I guess I'm proof that it's never too late to start learning thermodynamics. This cooler exhaust gas helps the nozzle, or usually the nozzle extension, be in contact with a cooler gas than if it were in contact with the main combustion chamber exhaust. You can see this utilized on the F1 engine that powered the Saturn V, as well as the Merlin 1D vacuum engine. And looking at the Merlin 1D vacuum, you can see streaks in its niobium alloy nozzle, which is radiatively cooled, but also takes the gas generator exhaust and uses it to cool the nozzle. The streaks are from little fins inside the exhaust manifold that maintain the structure. Side note, I used to think these streaks were from the pintle injector, but come to find out it's from the exhaust manifold support braces interacting with the film cooling. The other way to keep the walls of the combustion chamber and nozzle cool is by having additional fuel injectors along the perimeter of your injector plate. The injector plate is generally the entire top of the combustion chamber and is where the fuel and oxidizer mix, hopefully really well, and where the primary combustion occurs. I'll do an in-depth video on injectors here soon, but for now, just know in general, they mix to a predetermined amount of fuel and oxidizer, which balances performance and heat. The further away from their ideal ratio the fuel and oxidizer are, the cooler the combustion will be. Since oxygen is a heavier molecule than most fuels and can't be accelerated as quickly as a lighter fuel molecule can, engines tend to run fuel rich, and they change the ratio in order to control the temperature and performance. And in order to locally cool, say, the outer perimeter of a combustion chamber, where the exhaust comes in contact with the chamber walls, you can add a few more fuel injectors, so there'll be a layer of more fuel-rich exhaust that's in contact with the walls. The most problematic part of a rocket engine is the throat. This is where the heat absorbed by the wall of the nozzle is the highest. Luckily, this high temperature exhaust is only coming in contact with a small amount of surface area, and with a finite amount of cool fuel being pumped through the walls, having only a small area in contact with the hot exhaust gas is a good thing. Now, this is kind of backwards from what we normally tend to deal with in life. If you want to cool something off, you normally want a big surface area to radiate a lot of heat away, like a radiator does in a car. But that's not what's happening here. We have a heat source, and it's going to melt whatever it touches. Think about it like if you had a red hot fire going and you have a garden hose running to try to keep stuff you put in that fire from melting. Stick a metal rod in there a little, the hose will probably do a fine job in keeping the rod from melting. But if you put more and more of that rod into the fire, eventually the hose will not be able to keep up with the task of keeping the rod from melting. This is where a larger engine actually has a big advantage over a small engine. The volume of an engine, and therefore the amount of propellant per second in the engine, goes up by the cube of the engine's radius. But the surface area needed to cool the area only goes up by the radius squared. So larger engines have a lot more propellant to cool, only a little more surface area. Now let's make up some numbers here. Say the proportions of the engine are the same, but one engine has a throat diameter of 50 millimeters and one has a throat of 100 millimeters. The engine with the 50 millimeter diameter throat will have an area of 1,963 square millimeters and a circumference of 157 millimeters. The engine with a 100 millimeter diameter throat will have an area of 7,854 square millimeters and a circumference of only 314 millimeters. In other words, the 100 millimeter throat engine could flow 4 times more exhaust while only needing to cool twice as much surface area. But wait, it's still twice as much to cool, right? But guess what? If you're flowing 4 times as much exhaust through the throat, it also means you're flowing 4 times as much fuel as coolant through those areas as well. So really, in a sense, there's twice as much fuel as coolant to cool a given area when you double the diameter of your throat. That's a good thing. So a larger engine actually gets easier and easier to cool. But of course they start to bring on their own problems such as combustion instability, but in general, a bigger engine is easier to cool. And right here is the biggest problem with Aerospikes. By design, the throat of their combustion chamber has substantially more surface area to cool. For a toroidal Aerospike, the combustion chamber basically has a giant plug in the middle of it, which greatly increases the surface area of what needs to be cooled. Let's do some simple math based on those last chambers. Let's pretend we're trying to keep the same throat area of 7,854 square millimeters that we had with that 100 millimeter diameter throat. Well, in order to get that same throat area, we'd have to have, say, a 141 millimeter outer diameter throat and then a 100 millimeter inner diameter plug. This means we now have more than doubled the amount of surface area that we need to cool. We went from having a circumference of 314 millimeters to a circumference of both 314 millimeters plus an additional 444 millimeters for the outer diameter for a total of 758 millimeters. These numbers are a bit arbitrary here because we could really stretch this just about any way we want. But one thing that you can't overcome is the fact that you're inherently at least doubling the surface area at the exact place where it's the hardest to keep cool. But truth be told, engineers don't often suspend a plug in the middle of a normal combustion chamber. It's more common to make a ring for a combustion chamber. But even so, a ring still has an inner diameter and an outer diameter that you now have to cool. The J2T was actually a perfect example of this. It took the turbo machinery from a J2 engine and was put inside a toroidal Aerospike engine. But just look at this picture of the J2 versus the J2T. You can tell just how much substantially bigger the throat is, and now we have 2 throats of that larger diameter just to make up the same throat area as a standard J2. The math works out to being almost 15 times harder to cool the J2T than it is to cool a standard J2. That's certainly not trivial. And don't forget, you have to remove that heat somehow. If regenerative cooling through the walls isn't enough, you have to add more film cooling, change your overall burn ratio to cool all of the combustion chamber, or maybe use heavier or more expensive metals with higher melting points, any and all of these come at the expense of performance. Although we're still doing research on the combustion dynamics of Aerospike engines, but so far, they seem to be a few % less efficient at reacting to propellant in the combustion chambers, which wastes some of their highly cherishable chemical energy that's in the propellant. Now, of course, it's possible this all could be fixed with more work, but it could just be due to some of the many compromises required to make Aerospikes actually function, period. So really, the other thing that is a limiting factor for Aerospikes is weight. In general, it seems like Aerospikes have a much harder time achieving a high thrust to weight ratio when compared to their bell nozzle counterparts. This is mostly due to the larger amount of surface area for the combustion chamber or chambers, the additional plumbing to feed all the chambers, and the additional support and structures between the spike. Take a look at the XRS 2200 and look at how much stuff there is between the ramps. Although it seems like there'd be less nozzle, which may be true, there's honestly more of literally about everything else. Now imagine you had, say, a hydrogen leak in one of these additional tubes, pipes, or valves, which is really common because hydrogen's really hard to contain. There's just substantially more points of failure in an engine like this. And of course, weight is extremely important with rockets, and the thrust to weight ratio is a really important metric in rocket engines. After all, extra weight directly affects your payload capacity and overall performance of the rocket. So a lightweight and powerful engine is always a good thing. Another thing that can be difficult to do with Aerospikes is how to gimbal or steer them. Because of their large attachment points to the vehicle, it can be impractical to try and move the entire spike with thrust vector control. Although one good thing is, a gimbaled spike will never exceed its own perimeter, unlike a nozzle which can run into nearby engines. A common solution for thrust vectoring is to throttle individual chambers to perform differential thrust. By off-putting the thrust, it'll induce pitch or yaw to the vehicle. Although it's not as effective as steering the entire engine, it is a viable option. The RS2200 linear Aerospike was to use both actuated thrust vectoring and throttling. On the pitch and roll axis, it had actuated control, and for yaw control, it'd throttle individual chambers all the way down to 18%. And the last big deal with Aerospikes is actually their lack of real flight data. Now, although this seems like a simple solution or a perfect submission for the "Why Don't They Just" segment on our Ludicrous Future podcast that I'm a co-host of, I mean, why don't they just fly an Aerospike? Which, by the way, if you don't listen to our Ludicrous Future podcast here on YouTube or on your favorite podcast player, definitely get on that if you want your weekly fill of space news, EVs, futurism, etc., etc. Sorry, shameless plug. But the thing that hasn't really been proven out is what happens with Aerospikes between supersonic speeds, or above Mach 1, up to hypersonic speeds of Mach 5. And this is a non-trivial thing. But one really cool experiment was with the laser experiment, which was taking a scale mock-up of the X-33 tail and Aerospike engine, putting it on an SR-71 and flying above supersonic speeds. There were actually 7 research flights with the laser experiment on an SR-71, and although they never actually fired the engine, they did perform cold firing tests at Mach 1.58 and ground firings, which gave them all the information necessary to move on. But regardless of how cool it looks, the Aerospike engine still lacks any real runtime data in these supersonic and hypersonic regimes, or almost any real full-scale flight data, period. Okay, I think it's time we actually put up some Aerospike engines against more traditional engines and see how they compare. So let's start off with our lineup of traditional Bell engines. For this, we're going to be looking at the original J2, the J2S that was intended to replace the J2 engine. Then we'll look at the Space Shuttle's main engine, the RS-25, as well as SpaceX's Raptor engine. The reason I chose these engines is because they're substantial engines that have a lot of data. They're either alternatives to the Aerospike, the basis of Aerospikes, and or considered to be the best engines ever made. This way we get a variety of engines to compare different Aerospikes to, and each of these engines performs in the vacuum of space, or in the case of the RS-25 and the Raptor engine, they operate in space and at sea level like an Aerospike does. Now for Aerospike engines, we really only have 3 engines that really made it through a legitimate certification and testing program, but only 2 that I have good numbers on, and then there's 1 more engine that would have perhaps been the king of Aerospikes. So the engines with the most data that I could find were the J2T 250K toroidal Aerospike and the XRS 2200. By comparing these engines to the J2S, which they were based off of, we should get a pretty good idea of their performance. The other Aerospike we're going to look at is the RS-2200, which was the full-scale engine that would have actually powered the Venture Star. Now these numbers will have a pretty big asterisk next to them because this engine never actually hit the test stand, and it relied on a lot of new, unproven-ish technologies to get these numbers, such as lightweight carbon rams and ceramic tubes. So the numbers quoted here are what they would have needed to reach in order to make the Venture Star work, and truth be told, getting an engine to hit your targets can be very, very difficult. But the numbers on the Raptor are just the current numbers, and just like the Merlin engine, we do expect to see SpaceX continue to push this engine and develop it beyond these numbers in the very near future. And one more note, I should also point out that all of these engines are drawn to scale of each other. So let's start off with each engine's fuel. Every engine here runs on liquid hydrogen and liquid oxygen, otherwise known as hydrolox, except for the Raptor engine, which runs on liquid methane and liquid oxygen, or methalox. I wanted most of these engines to be hydrolox, so we're comparing the most apples to apples engines, since hydrolox engines have the most potential for a high specific impulse. But it's still fun to compare them here to the Methalox Raptor. Next, let's look at their cycles. And again, if you need a good rundown on engine cycles, I go into most of these in my video about the Raptor engine and its full flow stage combustion cycle. But the one engine cycle type that I didn't talk about is the tap-off method, which actually just uses the primary combustion chamber to power the turbine. And the engine here that uses the tap-off method is the J2S, which was intended to help simplify the engine and bring the cost down since it eliminated the preburner or gas generator. The original J2, the J2T 250K, the XRS 2200, and the RS 2200 all use a gas generator. The RS-25 is closed cycle, fuel rich, and the Raptor engine is, of course, a full flow stage combustion cycle. Now let's look at their thrust output. We'll do both sea level and vacuum thrust in kilonewtons. The J2 produced 486 kilonewtons at sea level and 1,033 kilonewtons in a vacuum. The J2S couldn't actually fire at sea level and in space produced 1,138 kilonewtons. The J2T 250K produced 731 kilonewtons at sea level, and it would do 1,112 kilonewtons in space. The XRS 2200 was 909 kilonewtons at sea level and 1,184 kilonewtons in space. The RS 2200 would have hopefully produced 1,917 kilonewtons at sea level and 2,201 kilonewtons in space. The RS-25 produces 1,859 kilonewtons at sea level and 2,278 kilonewtons in space. And the Raptor engine produces 1,960 kilonewtons at sea level and 2,150 kilonewtons in space. Now let's look at their efficiency, measured in seconds or the engine-specific impulse. You can think of this like the fuel economy of a gas-powered car. So a high specific impulse would be similar to a high mile per gallon or kilometers per liter. The best way to think of specific impulse is to imagine you had 1 kilogram of propellant. For how many seconds can the engine actually push with 9.81 newtons of force? The longer it can sip on that fuel while still pushing that hard, the higher its specific impulse, and therefore the more work it can do with the same amount of fuel. In other words, it's fuel economy. So the higher the specific impulse, the less fuel it takes to do the same amount of work, which is a good thing. A fuel-efficient engine is extremely important. The J2 was 200 seconds at sea level and 424 seconds in space. The J2S couldn't fire at sea level and was 436 seconds in space. The J2T was 290 seconds at sea level and 441 seconds in space. The XRS 2200 was 339 seconds at sea level and 436 in space. The RS 2200 was planned to have 347 seconds at sea level and 455 seconds in space. The RS 25 is 363 at sea level and 453 seconds in space. On the Raptor engines, 330 seconds at sea level and 355 seconds in space. Now, as we mentioned previously in the video, a huge factor in the specific impulse of an engine is the expansion ratio. So let's see if there's a strong correlation between expansion ratios and their specific impulse. The J2 was 27-1, the J2S was 40-1, the J2T was 80-1, the XRS 2200 was 58-1, the RS 2200 would have had a crazy 173-1, the RS 25 is 69-1, and the Raptor is 35-1. It should be noted that although the J2S has a higher expansion ratio, its dimensions look almost identical to the J2. That's on purpose. It's because the throat diameter is actually smaller on the J2S compared to the J2 in order to increase the expansion ratio, but also to keep the same general dimensions, which would make it a drop-in replacement to the J2. And lastly, let's look at their thrust to weight ratio. Now, this one we definitely need to remind you that these numbers could be off by a little bit, as each company might quote the engine with varying amounts of hardware or have different metrics for this. But in general, we can use these numbers as a decent rule of thumb. The J2 was 73-1, and although the J2S was simpler with no pre-burner, it was a little heavier and had a 69-1 thrust to weight ratio. The J2T was 63-1, the XRS 2200 was 35-1, the RS 2200 was planning to hit 83-1, but would have needed to hit 75-1 in order to make its SSTO capabilities possible. The RS-25 is 73-1, and the Raptor is 107-1. So now that we have all of these numbers, we can really see how Aerospikes compared to more traditional engines. And in general, the J2T and the XRS 2200 should be compared to the J2S, since that was really what was meant to replace the J2. And when we do so, we can definitely see why both of these engines were advantageous. They offer great vacuum performance, and they can still be used at sea level, something that the J2S physically couldn't do. And in this case, the J2T even seems to have been a better choice for an upgrade to the J2 than the J2S in literally every metric except for thrust to weight ratio. It was really a compelling option. And now when we compare all these to the Raptor engine, we can clearly see that the Raptor engine with a sea level nozzle and methalox isn't nearly as efficient in a vacuum, but with a mighty impressive thrust to weight ratio and solid sea level specific impulse, it's sort of out there on its own. Now, had the RS 2200 actually made it through development and truly hit all of these numbers, it would have been a very impressive engine. Not only does it have the best vacuum efficiency, it also would have managed to beat the RS-25's thrust to weight ratio. That being said, I've actually heard from multiple sources that had Lockheed Martin just simply stuck with the RS-25 for the Venture Star, it would have been just as good of an option and was already a complete engine, compared to the RS-2200, which would have still had a full, risky, and costly development ahead. But now with that in mind, I think it's time we hear from some real experts who have either worked on Aerospikes or who have opted against using them. So I actually reached out to Tori Bruno, the CEO of ULA, who actually worked on the X-33 and the Venture Star program, to hear what he has to say. The toughest part about the design and operation of an Aerospike engine is thermal management. A traditional Aerospike engine is conical in shape and can really struggle with heating as the spike tapers down. The linear Aerospike design, together with the strategy of truncating the taper, goes a long way to simplifying this problem, but it is still there. I also asked Tori if he thought the RS-2200 engine could have actually met the metrics it was intended to hit. He said, "I'm sure the engine would have worked and been practical. The complexity of so many separate engines, however, would have presented a weight growth challenge as well as significant propellant flow management complexity." And I just had to ask if after working with Aerospikes, if he loved them or hated them. I love them. Aerospikes are just plain cool, and linear Aerospikes are the coolest type. I agree, Tori. I also asked Elon Musk why he hasn't opted to use an Aerospike engine for anything at SpaceX, and here's what he had to say.
I've internally asked this question so many times, like, guys, shouldn't we maybe do an Aerospike? You got to get your combustion efficiency. There's really two parts to, like when you have a rocket engine, what are you trying to do? You're trying to shoot things out as fast as possible in a straight line.
Yes. Yep. Converting as much thermal and pressure into kinetic energy.
Yes, exactly. Possible. So you have your combustion efficiency. So what percentage of max theoretical combustion efficiency are you? Mm-hmm. And then what's your nozzle efficiency, which is really, are you straightening the flow and shooting the molecules out in a straight line so that you go in the other direction?
Yes.
Newton's third law.
Yep.
With a traditional combustion chamber, you can get to a very high combustion efficiency because the molecules are all sort of bouncing around in there. They've got time to combine and do their thing. And then when you sort of choke it through the throat, that gives them sort of more opportunity to combine.
Yep.
So we think we can probably get to 90, certainly 98.5 hopefully 99% of theoretical combustion efficiency. This is so if God himself came and knitted together the molecules to do 1% better. Okay, maybe 1.5% better. That's very high efficiency.
Because of full flow stage combustion.
Full flow stage combustion, exactly.
Yeah.
You've got a gas-gas interaction. So you've got two hot gases combining.
Yeah.
And with a relatively simple reaction, the only thing that would be simpler would be hydrogen. You actually want to say, what is the actual achievable combustion efficiency times the theoretical chemical energy? That's the real number.
Right.
And this is where methane starts to look really good.
And so you don't think, you're just telling me now, spoiler alert, you're probably never going to see a full flow stage combustion cycle Aerospike engine produced by SpaceX.
You know, if somebody can show that we're wrong, that would be great.
Yeah.
You know, if somebody can explain, like, wow, there is a way to make your design better. This is a gift.
Right.
I would be like, thank you for this great gift. Wow, this is awesome. It's definitely like the worst thing would be like we want to do some dumb design and stick with our dumb design.
Right.
That would be insane.
Right.
So I would love it if somebody could show how an Aerospike is the smart move. In which case, we'll just do an Aerospike.
Yeah, just do an Aerospike.
Yeah.
Aerospikes with Elon Musk.
So to summarize what Elon was saying, clearly him and his team are focusing first and foremost on combustion efficiency over other things like, say, an altitude compensating nozzle. And the other person that I think has some cool expertise on the subject is Peter Beck, the CEO and co-founder of Rocket Lab. Because not only has Peter Beck built Aerospikes himself, but he has a great view of why a company like Rocket Lab hasn't pursued them.
Why not Aerospikes? Why haven't Aerospikes been flown? Did you look at them? Is it something you would love to do at some point, or what? Tell me the actual rocket builders.
The curse of the Aerospike.
Yes.
Yeah.
Where's our Aerospikes?
I've got an engine out there that's an Aerospike. I mean, I've done my time on Aerospikes myself.
Really?
Yeah. I mean, so they're attractive. For all of the right physics reasons, but a pain in the ass for all of the engineering reasons. And it kind of cancels itself out. I mean, if physics says it's better, but engineering, trying to engineer them, it's far more complicated. And the mass and complexity you end up driving into them, and this is my own personal experience, driving into them versus just a typical conical bow, it's just not worth it.
So you physically are adding mass to potentially gain a little bit of
you end up in the same point. In my experience, you end up exactly in the same point, except with a much more complicated system that's unproven.
And I think cooling has always been a big issue because it's really hard to do that in the middle of middle of it.
And then it's other things like TVC. It's very easy to gimbal a chamber, piece of cake. But a whole Aerospike, do you gimbal the whole Aerospike, or do you have a multiple port Aerospike where you just throttle the Aerospike? And then what about all the altitude compensation effects and that you get? I mean, you have the same kind of complexities with multiple engines, the plume-plume interactions, as you're ascending through atmosphere, you've got all those plume-plume interactions and the plumes are changing, and then, your control system's changing as well because, the TVC works, functions differently at different plume-plume interactions and recirculation zones, and it's all a pain in the ass. But it's still less of a pain in the ass than something like an Aerospike, in my opinion.
Yeah.
Yeah, and the other thing to think about is that, if we were a lab, maybe that's a pure research lab, it's a different story. We're a commercial company.
Right.
We need, R&D is not fun anymore. R&D is just expensive and time consuming.
Yeah.
So, pick your battles.
And while I was sitting there chatting with Peter, it made me realize that the Electron uses 9 engines. And I wondered if they could do anything like gimbling inwards to utilize some sort of Aerospike-like effect. Here's his response.
Even we know if all your engines are able to thrust vector control, is it advantageous to actually aim them into the center near MECO or anything, as they get closer to the vacuum of space, or does that not really?
Oh, there's stuff you can do.
I may have just figured some stuff out.
Interesting. So there might actually be something there. I mean, I've heard that the Falcon 9 does something like that too. It's pretty cool that those companies are able to use multiple engines to do kind of an Aerospike-like effect. But perhaps the best summary of the Aerospike engine comes from Vector Aerospace, who worked on several Aerospike engines, including one of their first engines in April 2002, which was test fired in front of Elon Musk and Tom Mueller of SpaceX. The engine unfortunately only lasted 200 milliseconds before it blew the graphite plug right off the injector face, but this wasn't their last attempt. They continued to pursue different Aerospikes, including a 10-chamber, 1,300-pound thrust Aerospike engine, which also unfortunately failed on its 2009 flight test. In 2016, Vector released this statement, which I honestly think summarizes Aerospikes perfectly. While Aerospike engines can provide performance advantages, the larger number of parts and components means that they are usually heavier than their regular bell nozzle counterparts in terms of thrust to weight ratio, and more importantly, require very high component reliability. So the general consensus I've gotten from people who have worked on Aerospikes is it's just not worth it. Not only is the development and research costly and risky, but the net gain might not be any better than a more conventional tried and true Bell engine. And this is echoed when you learn about Firefly Aerospace, who had a really promising Aerospike engine known as the FRE2, which is to be a 12-nozzle methane-powered toroidal Aerospike engine that was to power their Firefly Alpha. After a company reset, the Aerospike plans died, and now the company is planning to utilize a traditional Bell nozzle as well. What's going on? Where are our Aerospike engines? So how many companies are currently working on Aerospikes as we speak? So far as I can tell, one-ish, kind of. Well, maybe two. Arca has a pretty intriguing video series called Flight of the Aerospike, and they are promising to make a low-cost and simple SSTO Aerospike rocket. But oddly enough, the latest video in the Flight of the Aerospike series shows the company testing their brand new systems using a traditional Bell nozzle and simplifying their rocket to run on steam. Now, I want this company to succeed, and I really want them to fire off their linear Aerospike, but from what I can tell, they've got a very, very long ways to go before they would ever be close to flying one. And although the company's been around for 20 years and has yet to fire an Aerospike, perhaps they'll make some progress and get something flying someday. But I'm starting to think this too will fall into the, well, it turns out it wasn't worth it category. The other company that's working on an Aerospike is Rocketstar, who's pursuing an Aerospike, but so far their engines seem to be only in the high-powered model rocket category. Although they do have plans for a Star-Lord rocket, which would use an Aerospike, but this is very much a paper rocket so far as I can tell. But Aerospikes still have some promise, right? I mean, most of the concepts we looked at utilize the open cycle or gas generators. Couldn't there be ways to improve upon Aerospikes that would make them more worth it? Well, there's two pretty promising ideas or technologies that might actually help Aerospikes find their place on the bottom end of an orbital rocket. The first being 3D printing. 3D printing allows for advanced designs that can help make cooling channels and combustion chamber shapes that would normally be physically impossible to manufacture, super easy to manufacture just by pushing a button. There's companies like Amero, I think that's how you say it, who have built additively manufactured Aerospikes out of Hastelloy X, which is a high-strength nickel-based superalloy. It's really cool to see how they can print these crazy shapes that are required for Aerospikes. The other concept that very well might work hand in hand with 3D printing is a dual expander cycle Aerospike engine, and one in particular is known as the dual expander Aerospike nozzle, or DEAN. What's cool about DEAN is it takes the biggest problem of Aerospikes, which is heat, and makes use of it in the expander cycle. The expander cycle is where a rocket engine takes the liquid fuel that cools the chamber, heats it up to the point of phase change, turning it into hot gaseous fuel, and then using that to spin the turbine, which will then power the engine. The problem with the expander cycle is actually the opposite of Aerospikes. They have a thrust output limited based on how much liquid fuel an engine can actually heat up and turn into gaseous fuel. So due to the square cube law, you eventually run out of surface area to heat up the fuel. The theoretical limit is approximately 300 kilonewtons of thrust before the surface area to volume of fuel ratio gets to the point where you can no longer power the pumps adequately. But by having more surface area to heat up fuel, like an Aerospike engine inherently has, you can actually get away with a more powerful engine, which might be a cool trick for future Aerospike engines. But to date, the DEAN concept has only existed in theoretical papers, which targets an engine with 111 kilonewtons, 383 seconds of impulse in a vacuum, and a thrust-to-weight ratio of 108, which I should note, those specific impulse and thrust-to-weight ratios put it right on par with the Raptor engine. But again, research papers and actual working hardware are very, very different things, which is why many of these concepts are studied only in research labs and often don't make it much further, nor do they end up being commercially viable. For now. Okay, wow, you're still here with me. This ended up being a lot longer video than I would have ever imagined, so let's do a quick summary. Aerospikes. Super cool on paper, a super tantalizing concept that seems to beckon even the most astute rocket engineers. Perfect for your SSTO concepts that might also need to be reconsidered, and likely to drain your bank account and make you age a few decades trying to develop it. But they are super cool, and as manufacturing and material sciences advance, perhaps we'll see companies able to utilize and exploit their advantages and close the gap on the Bell nozzle, which has dominated the aerospace industry. But perhaps the biggest reason why we generally don't see too many Aerospikes popping up in modern times is simple. If they truly offered a clear performance advantage, I would assume everyone would be developing them. But the fact of the matter is, they kind of wind up right back in the same place as a normal rocket engine. Now you could probably try and say the exact same thing about SpaceX's Raptor engine, which utilizes a full flow stage combustion cycle. That was considered far too difficult to really ever be worth it previously, and that rocket engine is extremely complex and unbelievably hard and expensive to develop. But the thing is, the full flow stage combustion cycle is just physically the best way to extract all your energy from your propellant. I mean, they actually perform better in virtually all metrics than other rocket engines, period. Whereas the Aerospike might gain some advantages in, say, altitude compensation, but it lacks advantages in other areas, which puts it right back on par with other engines. So as far as where to spend your time in research, that's why most engineers have pursued things like closed cycle engines, full flow stage combustion cycle, or the path of easiest manufacturing and development, like Rocket Lab's electric pump-fed engines. And just another note here while we wrap up about Aerospikes, and this is kind of similar to how I ended my SSTO video. It's not really the Aerospikes that suck, but it's their application here on Earth that sucks, because Earth is kind of just the wrong planet to utilize them. Ironically, if Earth's atmosphere was any thicker, the Aerospike would actually become significantly more advantageous, even for a multi-stage rocket. But with Earth's atmosphere as it is, the Bell nozzle is just too close to the same performance, making it a much easier and less risky choice in the aerospace industry. If it wasn't for their thermally backwards nature, their advantages may actually outweigh their disadvantages. But perhaps their tendency to melt themselves is the biggest reason why we just simply haven't seen one leave Earth's atmosphere. But all in all, I think the best way that I can summarize the Aerospike is to compare it to the rotary engine seen on cars like the RX-7 and the RX-8 and their predecessors. For those of you familiar with car engines, you may know about the rotary engine. They're super simple. There's only 3 moving parts. They're small, lightweight, and very powerful. On paper, the rotary engine really should have been a more popular choice in the automotive world. But in practice, they're a nightmare to cool and lubricate and have awful fuel economy and poor lifespan and reliability. That being said, they've maintained a major cult following, and in some aspects, they're still a good choice. People have always argued that if there is as much engineering put into the rotary engine as there has been for the piston engine, maybe the rotary would be about as efficient and reliable as a piston engine. And in the same way, sure, maybe the Aerospike could improve and be a more viable choice with an increase in research and development. But much like the rotary engine, would it really be worth it? Would it really ever truly be better than the alternative? The art of rocket engineering is balancing all of your variables, not only in performance, but also reliability, cost, development risk, manufacturing, and tying them all together to make the right choice for your vehicle. So at the end of the day, an Aerospike's biggest advantage is being able to fire a vacuum optimized engine at sea level. But in all reality, why do you want to do that? Unless you're, for whatever reason, required to do an SSTO, you really would never need to do this because it's much easier and much more common to just fire a sea level engine on your first stage and a vacuum optimized engine on your upper stage. So what do you think? Do you think Aerospikes are just too cool to ignore? Think we'll ever see one propel a vehicle into orbit? Or do you just think the bell nozzle is the right choice? Let me know your thoughts in the comments below. And be sure and let me know what other questions you have about Aerospike engines, rocket engines, or rocket science in general. And be sure and stick around because I have a perpetually growing list of awesome videos, and I'm trying my hardest to crank them all out. Special thanks to Charlie Garcia for chatting with me for hours and hours about Aerospikes and helping me grasp a lot of these technical points. He's my go-to personal, actual rocket scientist, and he has an awesome YouTube channel as well. So definitely go check it out and start learning even more in depth with Charlie Garcia. And I owe a really big thank you to Martian Days on Twitter. He did those beautiful engine renders, and he worked really, really hard to make sure they're perfectly in scale with each other. And of course, I owe a huge thank you to my Patreon supporters. If you can't tell, I'm constantly tweaking and trying to upgrade my stuff. So better video, better audio. I flew myself down to Mississippi to make sure I had the best footage of an Aerospike engine. I just think I'm trying to make the best product possible, and especially with my Patreons in our Discord channel, who literally helped me piece all this stuff together. And I owe a special thanks to Ghostwriter, who helped me dig through literally dozens of research papers. There's a couple others too, but you guys just keep me sane through all these times. So I owe the biggest thank you to you guys. If you want to help contribute or add your own facts or opinions, or just fact check our stuff as I research it, go ahead and consider becoming a Patreon supporter, where you'll gain access to our exclusive Discord, our exclusive subreddit, and even exclusive live streams as well by going to patreon.com/everydayastronaut. Thank you guys. And of course, while you're online, be sure and check out my web store where you can find things like this. Limited edition Aerospike engine shirt. We do limited runs of shirts and merchandise these days, so if you see something in that store that you like, you better get it right now because there's a good chance we'll run out of stock and we might not restock it. So literally, like the full flow stage combustion cycle shirt, every time it's in stock, we sell out right away. So if you see something in stock, you better get it today because it might not be there tomorrow. And don't forget, if you work in the aerospace industry, I actually give you 25% off all apparel as my thank you to you for helping inspire me and also for helping get humans off of this planet. And definitely be sure and subscribe to our Ludicrous Future podcast. That's the podcast that I'm a co-host of, where each week I give you your rundown on space news. So if you want more of me and you're like, Tim, your videos take months to make, trust me, I know. If you want to hear more from me every single week, you can listen to Our Ludicrous Future right here on YouTube or on your favorite podcast player as well. Thanks, everybody. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.